I wanted to talk a little bit about how to solve problems where we have to treat objects as a system rather than treating the objects separately. Now, this often seems like a really strange and foreign idea, uh, given that we're taking two objects that we can clearly see are separate objects, but we're treating them as though they're not separate, they're one object. But in reality, you actually have been doing this all along. So if we had just one box shown in this diagram with some force acting on it, you treat that box as though it's an object, but it's not. The box is made up of atoms, and the atoms are made up of protons and neutrons and electrons, and there are forces that exist between all of those different parts. And we're saying there's only one force, and that it acts, or I guess a few forces here, the tension force maybe to the right, and then gravity down and normal force upward on this. Maybe friction would be a part of that, but we're treating that collection of atoms and protons and neutrons and electrons that make up the atoms, we're treating those as though they're one big object with just a few forces acting on them. We're doing the same thing when we do these systems type problems. The only difference is that the things that we would usually consider objects are bigger than the objects in the previous example where the objects were atoms. So there's no reason that we couldn't group these objects together. So in a problem like this, let's say we want to figure out how fast these two accelerate. We've got a 10 kilogram box and a 5 kilogram box in front of it. We're going to pull the 10 kilogram box with a 100 Newton force. There are two ways that I could approach this problem. I could treat the red box and the blue box like they're two separate objects. And if I did that, my red box would have an upward normal force, call that A, this one A and this one B. It'd have a downward gravitational force. We've got this forward force, which is 100 newtons. And then box B is pushing on it, so we'll call that force box B on box A. And then box B, we'd have a normal force upward. We'd have a gravitational force downward. And we've got just this forward force from box A acting on box B. And no tension force on box B there. And we could solve it this way. We could figure out the force between those two boxes, the force from A to B, and how big a force that would have to be, and go from there. But this is a much simpler problem if instead of having these as two separate objects, let's just think of them as one big object with a mass of 15 kilograms. And then we don't need to think about the forces between A and B. Those are like the forces between the atoms in each individual box. We call those internal forces, and they aren't going to affect the motion of the system as a whole. Only external forces, that is, forces that are caused by objects outside our system, only those affect the motion of the system as a whole. So instead, I'm going to look at this 15 kilogram object, which has a 100 Newton force to the right. It's got a normal force up and an overall gravitational force down. I don't really care about the up and down forces here, though, because it's only going to accelerate in the horizontal direction. So now at this point, it's a very straightforward problem. I do my Newton's second law equation. My net force is 100 newtons to the right. The mass is 15 kilograms, and the acceleration is what I'm solving for. And so then we do 100 divided by 15, and we get about 6.7 meters per second squared. Now we could take that number and put it back with either of these forces individually to figure out how big that contact force between them is. So let's look at block B, the blue one here. The net force acting on block B will be equal to mass times acceleration. And then the net force here is just going to be that force from A acting on B. There's only that one force in the x direction. is equal to the mass of block B, which is 5 kilograms, times the acceleration of block B, which is 6.7 meters per second squared. And so we get a force from A on B of 33.3 newtons. And then the force from B on A, that's a third law pair, so that one would be 33.3 newtons as well, just in the opposite direction. But you don't have to take my word for it. We can actually solve for that one also. Kind of felt like LeVar Burton saying, hey, you don't have to take my word for it. Check out your local library. So on this one, I miss reading Rainbow. What a great show. We've got two forces acting on this one. We have force tension going to the right, and the force from B on A going to the left is equal to 10 kilograms times the acceleration in the x direction. We had our tension force was 100 newtons, minus, we said that's going to be 33.3 newtons, is equal to 10 kilograms, and the acceleration here is 6.7 meters per second squared. And so we'll do 100 minus 33.3, which is 67.7 newtons, equals 10 times 6.7 is 67, and I rounded off differently on these two. So the 6.7 was really 6.6 repeating, so and the 33.3 was really 33.3 repeating. So we end up with the same answer regardless of how we approach it here. So it doesn't matter which method you use or which box we examine. We find that this force between these two boxes is equal, or is the same value no matter how we approach it. But the big idea that we wanted to get to here was that it's okay to treat these two objects, these two boxes, as though they're one single 15 kilogram object, unless we want to investigate the forces that act between those objects, the force from B on A or the force from A on B. Then we have to treat those like they're separate objects. If you were asked to go even further and examine the forces exerted on a single atom within that box, or one of those boxes, which isn't a problem we'd be asked to do, but if we were, then our box we think of as the system, and we have to go down another level. But as I said, it's something you've already been doing, we just didn't recognize that we were doing it so far. So hopefully that helps a little bit. This is a problem that has, or a method that has wide-ranging applications, and oftentimes you'll find that you can avoid some fairly complex algebra involving solving systems of equations, things like that, by setting things up as systems of objects. So try it out. If you learned something from this video, please like it or share it with your friends. If you think you'll learn something from these in the future, go ahead and subscribe to the channel. And if you had questions or comments, please leave those in the fields below. Thank you much.